In this project, we studied fluid mechanics using expressions derived from Bernoulli's equation. It can be explained using schemes of a fluid in a cylinder with bases of different areas. This equation relates the pressure, the flow speed, and the height for the flow of an ideal fluid. It's important to say that this equation only works on certain situations, but it's easy to use and apply. P1 and P2 are the pressure, the Greek letter ρ is the fluid density, Y1 and 2 are the heights, and V1 and V2 are the speeds. Bernoulli's equation is complemented by the continuity equation, which expresses a quantitative relationship as the mass in the fluid doesn't change as it flows. In this case, A expresses area and V expresses volume. As in Bernoulli's equation, if the fluid is incompressible, the product of A and V is constant, and it has the same value at every point throughout the tube where the fluid moves. A multiplied by V also represents the volume flow rate. This is the rate at which volume crosses a section of the tube. We took into consideration all of these expressions to analyze our experimental model, in which we had a water jet coming out of a hole at the bottom of a cylindrical open container. The research objectives are to use expression derived from Bernoulli's equation to get information about an experimental model, compare experimental and calculated values of the range of a water jet versus time, and obtain the flight time of a water jet at the highest level of water and compare it with the value at the lowest.
We're gonna see our tube, and well, here we can see how the water is going through the little space we made, and well, in a certain time it's gonna finish the water it is inside of the tube. So we are gonna get those calculus with the theory and data. We have to identify our h, that is 0.31 meters, that is where the level of the water is, and our capital H is the distance of the table and the level of the water. That is 1.073 meters. So now we're gonna get the time. This formula we derived from the semi-projectile motion that we learned this in physics 1. So we have the formula of the velocity in y, and it's equal to the initial velocity y plus the acceleration in y multiplied by the time, and we cancel some factors, and now we can derive the t. We substitute the final y minus the initial y with our h. We have the capital H minus the small h over the gravity. So we know that the gravity is 9.81 meters over second square second, and we have that the time in our maximum height is 394 seconds. Sorry. Then we get the time with the minimum height until, well, there is a height that the water is not gonna come through, that we see in the video. So the time change and decrease. Moving on to get the theory range, we derived this formula with the velocity that it takes the water to get out multiplied by the time, and the formula gets like this. It's 2 square root of the small h multiplied by the difference of the two h, the capital one and the small one, and we get our experimental range of 0.97 meters. And we have our experimental range, of 0.94 meters. So if we get the difference, we can get that the theory range minus the experimental range, and the difference will be 3 centimeters. It is important to get the volume of our tube, and with this we get the area, and it's 0.00171 meters square, and the volume, you know that it's the area of the base multiplied by the height, and it's 5.309 multiplied by 10 power minus 4 cubic meters, because it's a volume. Now we are gonna get the volume flow rate. This is the volume that decrease in a period of time, in a certain period of time here, and the formula is the area of the small exit multiplied the velocity, that is the speed exit, and the time. The formula of the speed exit is the square root of 2 multiplied by the gravity and the small h, that is the level of the water. This is important because this h is gonna change in every 5 seconds. So, as we know, when the time is 0, the h is the maximum, that it's 0.31 meters. And we don't have any volume flow rate because the time is 0 and we don't, so the volume don't decrease. However, when it passed 5 seconds, we have a new volume flow rate, as we can see, that is 2.478 multiplied by 10 power of minus 5 cubic meters. How do we get this? Okay, we multiplied the area and the speed exit, the exit speed, and the 5 seconds that it passed. So we have the new volume flow rate. Then, to get the new h, that it's very important because every 5 seconds it's gonna change. As we can see here, it is important to remember the volume, the original volume of the tube, because we're gonna use it. Here it's the original volume minus the volume flow rate we get, for example, in 5 seconds. With this, we're gonna get a new volume, and it's equal to the area of the base multiplied by the height of our, for example, tube. So the new h is we can derive this and we get the new h. So the new h after 5 seconds, for example, will be 2.29 meters. So this h we will use to get the one of 10 seconds when we get the new volume flow rate, and so on, and you continue, and you have to get the new h every 5 seconds. We can see this graph. We compare the experimental results over the theory ones, and we can get that both shows an exponential graph. The difference between them are literally decimals, because in Excel it's more exact with all the numbers. So we get that with this formula we can say that we have the same results of the theory ones and the experimental, so we have very satisfactory results.
For better results in this project, we recommend avoiding air currents as they can affect the water jet's range and experimental measurements, making sure the tube's ends and perforated hole are even, setting the tube in a stable position during all the tests, and marking some centimeters on the tube to make measuring easier.
Finally, we conclude that there is a relationship between the height and the speed. It was verified, as well as the importance of the level of water to obtain the volume lost. In this case, is the volume flow rate. And after saying the recommendations, we also can conclude that the theory is proven with the experimentation.